Consider this problem where we're given the input signal x of t. It is an exponential signal times unit step, and we are drawing that signal as well. The red signal is x of t, and h of t, the impulse response is as shown. It is e to the negative 2t u of t. And we'd like to find y of t, which is given by the convolution between x of t and h of t. And the expression for y of t, the convolution integral is x of tau h of t minus tau d tau. And we are plotting the two functions as a function of t right now. And the first step in convolution is replace t by tau. So what we're going to do is redraw the graph so that the independent variable is tau. So we're going to replace all t's by tau. That's the first step we do. The second thing we do is we time reverse h of tau. So as we do that, what we're going to see is x of tau doesn't change, it remains fixed. And we are reversing just the blue one. Which will look like that. And the third step in convolution is shift h of negative tau. So right now what we have is h of minus tau and x of tau. Now what we're going to do is apply a shift to h of minus tau. Okay, and since h of tau has been reversed in time already, as we apply negative shift, we have to move it to the left. And if we apply any positive shift, we have to move this function to the right. And we have to consider all shifts from negative infinity to plus infinity. And we represent the shift by t. Okay, now as we shift this signal or the function h of minus tau, what kind of interaction do we see between the two functions? So first, let's write down h of t minus tau, and x of tau is still the same function. We haven't changed it. Then we move this a little over here. So let's say this is 0. And so before, when we haven't applied any shift, our function, the blue function, is right over here. That is before we apply any shift. So the shift is 0. That is t equals 0. And what we're going to do is apply a shift of negative infinity and then gradually increase the shift all the way to plus infinity. So when the shift is negative infinity, that is t equals negative infinity, the blue function is all the way to the left. And as we slowly increase the value of t, this function starts moving to the right. And when we get to a shift of 0, then we get to this point, right? So after this point, further increasing t will cause an overlap between the two functions. So we see partial overlap between the two functions, and the overlap keeps on increasing as we increase the value of t. And this trend will continue until well, all the way up to infinity. So there are two important, there is one important time value that we should notice, we should mark, and that is 0. Before shift is, when shift is less than 0, there is no overlap. When shift is greater than 0, there is an overlap. Okay, so let's write down those two, just one important shift value, and we'll call it boundary. And that important point is t equals 0. And we always add negative infinity and plus infinity to the list of boundary points. And in this case, we just had one, which is 0, but sometimes we have more than one. Okay, and now based on these boundary points, we are going to split the shift range, which is from minus infinity to plus infinity, into various segments. The first region will be from negative infinity up to 0. The second region is going to be from 0 to infinity. In the first region, there is no overlap. And in the second region, there is always some overlap. And as we evaluate the convolution integral, we have to consider these two regions separately. So let's consider the first one. And let's draw a figure that would represent the first case. Okay, so we need to draw a graph for t less than 0 case. Let's draw it like this. And then if we look at the convolution integral, we have x of tau times h of t minus tau d tau. And what we see from the graph is that the blue function is non-zero in this range, and the red function is non-zero from 0 to plus infinity. And their non-zero segments do not overlap. So the product is always going to be 0. And as we integrate something that is 0, the answer is going to be 0. So this is the expression for y of t. It is 0, and it applies only to this region. And we have to now consider region 2 separately. Okay, so let's draw a graph to show how the two functions look like in this region. So this is the case where we see some overlap. And the point that was initially at 0 before any shift. So before any shift, the graph looked like this, and the right end of the blue function was at tau equals 0. As we move this function, the point that was initially at 0, it becomes t. Okay. So this point is t. So remember that. Now we need to consider, we need to find the overlap range. So the overlap begins at the left end of the red function, and it ends at the right end of the blue function. So this whole region, which we're going to shade, right? So the shaded portion is the overlapping range. And now we consider the convolution integral. Okay, let me copy this from over here. Okay, so the range of overlap beginning point is 0. That becomes our lower limit for the integral. The overlap endpoint, which is t, becomes our upper limit. And then x of tau, the expression for x of tau is right here. We can actually copy this. And the expression for h of t minus tau. Well, since the expression for h of t is e to the negative 2t u of t, the expression for h of t minus tau equals e to the negative 2 t minus tau u t minus tau. So we are basically replacing every t by t minus tau. Okay, so let's copy the expression for h of t minus tau. So in the range that we are considering, u of tau and u of t minus tau is always 1. So this is going to be 1. This is going to be 1. So we have e to the negative tau, and then we have e to the negative 2t. We are splitting the second exponential and d tau. So I forgot d tau over here. I don't know where this t is from. Okay, now, since we are integrating with respect to tau, this is a constant, so we can pull that out. And we have e to the negative tau and e to the 2 tau. We can combine them and write them as e to the tau. And if we do the integral, now we get e to the tau, and the integral limits are 0 to t. Applying those limits, we get e to the t minus 1. And distributing the outer exponential, we get e to the negative t minus e to the negative 2t. So we have the expression for y of t in this region as well. Overall, the expression for y of t is 0 when t is between negative infinity and 0. And the expression is this when t is between 0 and infinity. And then we can always do sanity check. So two things we can check are, first, the range, the non-zero range of y of t. So if we look at the range of x of t is non-zero from 0 to infinity, and h of t is also non-zero from 0 to infinity. So what we should get is that with an abuse of notation, I'm going to do this. So the range of y of t, the non-zero portion, should be from 0 plus 0 is 0 to infinity plus infinity is infinity. And this is what we actually got. The non-zero portion of y of t is from 0 to infinity. So the range checks. Now we'll see if the boundary values are correct. So let me copy this. Copy. And so we have only one boundary point, which is 0. So the time 0 appears in both rows. So if we evaluate the second row at t equals 0, we get e to the 0 minus e to the 0, which is 0. And if we evaluate the top row at t equals 0, it is always 0. So the two boundary values also match. So that means we didn't find any error. And this is our answer for the convolution between x and h.